Principle of radiation detection and monitoring. Radiation detectors. Radiation cannot be seen, feel, or detected by our sense, or we need special instruction called radiation detector or measure it. Every radiation monitoring device has two main parts: a detector, which is a sensitive material, and a measuring system that records the reaction. When the radiation interaction with the detector, it produces measurable effects. One common effect is ionization, where atoms lose electrons and form ion pairs. This ion pair can be collected to produce an electrical signal which tells us how strong the radiation is. Some detectors work by producing light flash called scintillation when radiation hits them. By counting these light pulses, we cannot measure radiation intensity. Other detectors can store the radiation effect and give result later, for example film batch or TLD. All radiation detectors work based one simple idea: radiation deposits energy in the detector and this energy is converted into a measurable signal. This instrument can be designed to measure rate of radiation, which is how fast radiation is coming, and the total radiation dose, how much radiation over time. Type of radiation detectors. The commonly used type are gas field detector, which is ionization chamber, proportional counter, GM counter, which is work by ionization gas, scintillation detector, which is metal, produce light when radiation interact, photographic detectors or film based, store radiation effect as blinking, solid state detectors, semiconductors, thermoluminescent dosimeters, high sensitive and accurate. Gas field detectors. Gas field detectors are one of the most commonly used radiation detectors. They work by using a gas like air or special gas inside a chamber to detect radiation. When radiation passes through the gas, it causes ionization. Measuring gas molecules lose electrons and form positive ion and free electrons. This charge particle are used to detect radiation. Working principle of gas field detectors. A high voltage is applied between two electrodes, cathode negative and anode which is positive. When radiation enters the detectors, it ionizes the gas molecules. Positive ion move towards the cathode, electron move towards the anode. These charges are collected by the electrodes. This movement creates a small electrical current. This current is very small, so sensitive measure device is used to detect and display it. Region of operation. Region of recombinations, which is A and B. In this diagram, so the level of A and B A and B region, a low applied voltage, some of the ion pair recombine to form natural atoms. The recombination decreases as the applied voltage is increased. Hence, the number of ion pair collect increase intensity when applied bias. In this diagram shows the A, B, C, D, E, F, G region. The ionization chamber region B or C, B to C. When further increase in voltage, all ion pairs are collected, band this, and the number of ion pair produced and collect remain constant independent of voltage but dependent of energy deposit in the detector volume by radiation. Detector operating in this region are called as ionization chamber. In this region, B and C are called as ionization chamber region, which is NO voltage is between 200. Region of proportionality D to E. The negative ion, usually electrons, in their path towards the central electrode are accelerated because of high electrical field in the vicinity of central electrode. Electron gain sufficient energy to produce secondary ion when the interaction with gas molecule. This result in the increase in the number of ion pair collect when it is proportional to the energy displayed by the incident particle. The constant of proportionality amplification increase with increase in the applied voltage and may be high as 10410 less than 4101. In this region, the size of pulse produced by the detector is proportional to the number of primary ions generated by particles. This is the proportional D to E proportional region. Region of limited proportionality E to F. In this region, the amplification is not constant because of space charge alert the shape of the electric field. The pulse height does increase in a linear fashion with energy deposit. This region is not generally used for radiation detection. Or E2F, which is not used for radiation detection. GM region or gigamolar region F to G. As the voltage is increased further, the sensitivity of region spread over the entire length of chamber. This is not different in pulse height for particular of different energy and types. The amplification factor may be high as 10810 greater than 8108. These detectors are very sensitive and are called as GM counters. F to G is the F to G region is the GM counter region. Region of continuous discharge band G. At the very high voltage, continuous discharge occurs and spark takes place. This region is not suitable for radiation detection. Detectors. Ionization gas field radiation detectors. which is first ionization chamber. This is a diagram of a ionization chamber. The ionization chamber is a very versatile device. It can be designed in many shape and size with different gas fillings. The gas used is generally in air at atmospheric pressure. The wall material should have radiation absorb and scatter characteristics identical to the air. Ionization chamber is also used for personal monitoring. It is called pocket dosimeter. It has built-in capacitance which can be charged. When exposed to radiation, ionization decreases the voltage across the capacitor. The radiation in voltage is measure of radiation exposure. Which is the ionization chamber diagram, which is gas chamber, which gas field and ionization radiation current, which connect to a amplifier and a cathode plus minus and anode. Proportional counters. The gas proportional counter GPC is a gas field detector. The output charge is proportional to incoming radiation and energy. Which is gas field detector diagram. Anode were connected with filled with gas in both side cathode. Thin window is present which is connected to a battery with low resistance. GPC can detect alpha particle radiation, distinguish between them, detector gamma radiation, low energy, P10 gas, 10% region plus 10% methane is commonly used. Ziegler Moller counter. The GM detector is a gas field detector. Key point: detect alpha, beta and gamma. Produce large pulse due to gas multiplication. Very sensitive, simple, inexpensive. Used for contamination monitoring. Limitation: not suitable for higher radiation field. Limit range 0 to 50 mR per hour typically. Which types are pan catch and window compensated GM. Delay time and recovery time. Dead time and recovery time. Period during which detector can be record another event. Record time to return to normal operation. N is equal to M divided by 1 by M lambda, where N is equal to 2 count rate, M is equal to observed count rate, lambda is equal to resolving time. Solid state detectors. Scintillation detectors. This detects radiation by measuring light flash. Scintillation components. Scintillator produce light. Photomultiplication tube convert light to electric signal. Example NAL detector use gamma radiation. This is the material used in scintillation detector. Liquid scintillation counter LSC used for low level beta detection. high efficiency detection of alpha, beta and gamma. Working beta particle interact with liquid, energy absorbed, extraction, UV light emitted, converted to visible light, PMT convert light, electric signal, analyze, measure energy, key points, high sensitivity, used for titanium detector, expensive system, mostly laboratory use this type of detectors. Process and steps: beta emission, energy loss in medium, UV emission, blue light emission, PMT detector, signal analysis. Semiconductor detectors: the solid state detectors such as silicon and germanium detectors are mainly used for gamma spectroscopy. The main advantage of solid state detectors is very good energy resolution. This is because the average energy required to produce an electron hole pair in semiconducting material is about 3.5 eV as against 35 eV of air, resulting in the creation of large number of electron hole pair of given radiation energy loss in the medium. Gamma detector efficiency of germanium is low, but the energy resolution of gamma spectroscopy by germanium is best among all detectors. The operating temperature is very low and require liquid nitrogen to maintain operating temperature. Gamma emitting isotope identification and quantitation are the main use for detectors. The gamma spectroscopy system can be a fixed system or portable system. Normally, there are fixed instruments with a thick and heavy shield around detectors and simple to reduce background radiations. Thermoluminescent dosimeter, which is currently used for radiation detectors in personal monitoring. When certain solids are exposed to ionizing radiation, the electrons released in the ionization process are trapped at lattice imperfection in the crystalline solid. The electrons remain trapped till they are released by thermal ignition at some evidence temperature. They emit light in process, and the quantity of light emitted as the material is heated by measure and related to the absorbed dose material. The material thus exposed and heat can be released after proper analyzing. Many of thermoluminescent materials like LiFi, SO4, CaSO4, Ca have been study of this. Sulfur Dephlon has been found to be very useful for dosimetric purpose due to its high sensitivity, low findings in organic production and many other useful characteristics. Since the effective atomic number of LiFi is capable to that of tissue and air, it is found to be almost energy independent. This phosphorus is also widely used in both personal and monitoring as well as other dosimetric applications. Other TLD such as CaSO4, diphenol AI2O2 have higher effective atomic number and hence show significant energy dependent to X-ray and gamma ray. Hence material field have to be used to compose the dependence of resolution response on photon energy. The use of filters also permit the estimation of energy of photon below 200 keV. Chemical detectors. The chemical detector of interest has here is photographic emulsion or film base. Photographic emulsion consists of a sensitive layer of silver halide crystal in gelatin sprayed on the cellulose accurate base. The thickness of emulsion layer from 10 to 25 micron. On exposure to nuclear radiation or light, a latent image is formed on the film. Radiation exposure causes ionization in the silver bromide crystal or grain. A group of silver chloride containing silver atoms are formed in the surface of crystals. During development, each exposed grain is reduced to metallic silver. The developers serves many as reducing agent. The exposed silver halide crystals are dissolved by immersing film in fixed solution. The process film show baking and the amount of baking is released to quantity of radiation record. The baking is measured in terms of optical density. It is related to the quantity of radiation absorbed in the film. The optical density is measured using an instrument known as densitometer. The optical density produced by a given dose radiation depends upon its natural energy. In case of X-ray and gamma ray, the response per unit dose increase with increased energy reach a peak around 500 kV and decrease therefore to become almost band 0.5 MeV. Hence metal filters are used to comprehensive for energy dependence. The energy of photons below 250 kV is estimated from optical density record on the different material filters. Special photography film is combination with certain metallic filters are used in the personal monitoring. Radiation monitoring instruments. Radiation monitoring instrument can be broadly classified into three categories based on the application as area monitoring instrument, portable survey instrument and personal monitoring instruments. Since there is a wide variation in type, energy and level of radiation to be monitored, it often becomes necessary to use multiple instruments to monitor the radiological parameters. Monitoring device based on almost all the type of detectors mentioned in previous section are used in radiation monitoring. For accurate measurement of radiation dose, special ionization chambers which have uniform response to incident radiation of all energy are used. Instruments based on such ion chamber have accuracy better than ±5% and are normally referred to as dosimeters. The GM counter at some scintillators have different response of different energy of incident radiation and hence the instrument based on them have accurate on of the order of plus minus 10% or more. They are mainly used for general radiation survey, personal monitoring, and contamination monitoring. Apart from this, TL, phosphor, and photographic film can also be used as dosimeters. These are called as passive dosimeters since they require no power supply for operation and of integration type. Example, they keep on the accumulating the radiation dose unit. A readout is made. The instruments based on the ion chamber are normally expensive and delicate as the ionization current are very low, 10 to the power minus 12 ampere to 10 to the power minus 9 ampere. For the range of exposure from a few mR per hour to serve a R per hour, especially low current electrometer amplifiers are used. The required region maintained the GM counter based on instrument are rock, completely inexpensive and require little maintenance. Instruments based on the scintillators are also expensive and dedicated as they contain the photomultiplicator tube and normally used for measurement of low radiation level of the order of microrads to millirads. The passive dosimeter like TLD and other photographic film dosimeter are being used for regular personal monitoring and accident dosimetry. A practical instrument must be tell us how which type of radiation it is measured as well as the intensity. Each instrument mainly indicate that the radiation field in a work location is. This is engaged information to able us to a practical instrument must be tell us which type of radiation it is measuring as well as the intensity. An instrument may indicate that the radiation field in a work location is. This is not engaged information to enable us to access the hazard. For example, if the radiation being measured in gamma radiation, we know be exposed to an equivalent dose radiation of it the whole body. If the radiation is pure beta radiation, we would also be exposed to but would only get a shallow dose, not a whole body dose, also known as the radiation is due to beta ray would allow us to use relatively higher shielding to emitting the hazard almost entirely. If the radiation is pure beta radiation, we would also be exposed to but would only get a shallow dose, not a whole body dose. Also, knowledge that the radiation is due to beta ray would allow us to use relatively light shielding to emit the hazard almost entirely. If the radiation is pure, the alpha radiation, there is no external hazard, but we would have to take precautions to avoid ingesting the alpha emitting radioactivity. If the radiation is composed of neutrons, the dose rate would have been multiple by the appropriate radiation, which factor is given in the equivalent dose rate to the whole body. Uniformity: all radiation detectors respond to more than one type of radiation, so instruments have to be designed such that only the effect of this kind of radiation we were trying to measure are recorded. Generally, in mixed radiation field, a number of different instruments is required to measure the intensity of each radiation present. Instrument checks: in the last stage, we check the instrument for proper functioning and maintenance. It is important to check the radiation instrument periodically to ensure that they are calibrated correctly, which is per yearly calibrate, and before each use a pre-operational check should be made with consistent of following checks. Check that a due date on calibration sticker is not exceeded. Battery check and source check. If source is used in the detector or metal is used in the detector. Thank you for watching. This content is referred from Radiation Safety Certification course for radiotherapy technologists in the chapter of principle